Hello, everyone. Apparently, there are no viewers yet. Interesting. All right, we're about to start. Let me do a little bit of housekeeping here. Let's start my toolbox. Toolbox is on, and I will enter Twitter handle. So that should be visible now. Excellent. And I'm also going to add the Q&A box on here. I would prefer that you tweet questions to me via Twitter at Dionandan. My Twitter handle is there on the screen. And once again, I'm at a secure, undisclosed location, which may or may not be my parents' house in Toronto, so don't ask. Right, so what we're going to do now is we are about to go to the screen view for us to start the presentation. Before we do that, let me just see if I can do some special things here. Okay, it's not a live lecture without a pirate hat. We're ready to go. All right, so I'm sorry that we missed the lecture on Wednesday. As you may have heard, I had a little bit of a scooter accident and I had to go to the hospital, but I'm immobile, but I'm fine. And I'd originally planned to actually cancel today's lecture as a gift to you, but that can't happen now because we skipped Wednesday's lecture. So what we were going to cover on Wednesday, we're going to cover instead today. And that is the second half of linear regression lecture. And it's going to be relatively short, maybe 20 minutes. There's not a lot to cover, and I don't want to risk this medium going offline as we cover some new things. So we'll do a little bit of review of what we covered last time and just touch upon one or two new concepts. And then next week, we will continue with multiple regression, sample size calculation, and then the course is over. How exciting is that? Right. Hopefully we'll get a guest lecture in by the TA, Fadi Boris. He hasn't confirmed yet, but we'll see if we can make that happen. All right, so give me a moment here as I attempt to start the presentation. And again, if there are any questions or issues, tweet me right away at Dionandan. I can't access my email right now that quickly, but my Twitter feed is on, and I will see that relatively fast. Starting the screen sharing. So let us go here. And I'm here now. All right. So we should be able to see this screen called simple regression. And I'm going to start the presentation so it goes full screen like this. Right. So if you cannot see this, let me know right away. You should be seeing the first slide of the presentation called More Simple Regression. Excellent. Give me a second here. I actually have 4 computers open, and I'm accessing my other computer so I know what slide is coming next. All right. So as we covered last time, is the regression equation. All we're doing is we are attempting to model a relationship between two continuous variables such that it resembles a straight line. And our terminology used these elements here. Y prime is the predicted value of y according to our equation. X is the actual value of x from our data, and A is the intercept on the y-axis, and B is the slope, right? Which you also call the regression coefficient. Check my Twitter feed, make sure no one's asked me any questions. So far, no one's asked me any questions. Good. No questions is good. That means I'm being perfectly clear. That's a rarity in my life. All right. So the least squares method, what we talked about last class, is essentially this. If these are our data points, we're looking for the line that minimizes the total distance between the points and that line, measured vertically, like this. Why is that relevant? It's relevant because there's actually a lot of ways to do this. It doesn't have to be vertical. But that's what the ordinary least squares method attempts to measure, as this slide will show us. See, this is what we're doing, the usual model. We're looking at the distance between each point vertically from the straight line. And notice this has an intercept, right? There are other ways of doing it. We could have gone this way, right? Here, we actually have vertical distances as well, but there is no y-intercept. It goes right through the origin. People sometimes model it that way. Perhaps a more accurate method is this over here, where it's the orthogonal distances between the point and the straight line. So hopefully you can see the difference between this and that. It's here, this would be a right angle. Each of these are right angles. Here, they're straight lines that are parallel to the y-axis. Now, in this version of the orthogonal fitting, the line has a y-intercept. In this version, it goes through the origin. So there are a lot of assumptions that go into play when choosing which model to attempt to conform our data to. In these examples here, we're assuming the line goes through the origin. And very often that's the case. But this is a bit more forgiving. If we model it this way, if it does go through the origin, then our intercept reduces to 0. Here we force it to go through the origin. And in my opinion, the orthogonal fitting is actually more accurate than the vertical fitting. But this is what we usually do because it's easier and we can compute it much more simplistically. So we're going to do an example. And this example is hypothetical data that's loosely based on a study, a cross-sectional study. Remember that means, right? Cross-sectional means that we ascertain the exposure and the outcome simultaneously. It's like a slice in time, right? And this measured a relationship between vitamin D intake and some kind of cognitive function. Now, cognitive function here is measured by something called the digit symbol substitution test. I have no idea what that is. My first thought was it's a digital rectal exam, which makes no sense here, but hey, let's think of it that way because it's funny. So this study looked at 100 middle-aged men and attempted to ascertain, is there a relationship between cognitive function as measured by DSST and how much vitamin D they were taking in. So the first thing we do is we look at the actual variables. So the vitamin D variable is continuous. It's relatively normally distributed, skewed positively slightly, but it looks like a traditional continuous variable. And the DSST, or cognitive function variable, is also a continuous variable, perfectly normally distributed. So we know that both of these variables satisfy our requirements in that they are both continuous, somewhat normally distributed, and therefore representing a universe of normal distribution. So as always, we begin by doing a scatter plot of our two variables. And here we have this. What do you think? I think that the slide gives it away. There's no relationship here. There's no obvious way in which there is a linear or a curvilinear or some kind of curve that we are familiar with that describes the relationship between this variable and that variable. It looks pretty random to me. In another data set, looking at the same relationship, they got this instead. Okay, is there something going on here? Maybe. It's starting to look linear, but what I hope you're noticing is that so much of this is subjective, it's personal, there's a human component to it where, oh, that looks linear to me, therefore let's fit a straight line. To somebody else, that doesn't look linear, that looks like a blob of some kind, you know. In fact, it's probably these couple of guys over here that are forcing us to think of it as being linear because it's extending the relationship longitudinally. And in this next version, that looks even more linear, right? So one could conceivably plot a straight line here. Now, look back at the examples I gave you of the different ways of plotting lines. If one had gone for one that goes directly through the origin, you'd have something looking here, but probably your imagination is compelling you to draw it over here somewhere. So this would be something with y-intercept. And here we have an even stronger relationship. Now it's starting to look pretty linear. Again, if I were to take out just these two guys, you'd probably say no, there's nothing happening here. So this linear modeling is really dependent upon outliers and the contribution of a few points that may in fact sway the relationship one way or the other. Now, I want you to go back to this one here. This one has no relationship. Now, if you were forced to draw a line here, you would probably draw it in the middle here somewhere. So let's do it. If we actually used our equation and modeled a line through that glob, you would get this. You'd get a slope of 0. And that's what we're always finding, is that if there in fact nothing going on, if it's relatively randomly splayed across the page, the straight line equation, or this ordinary least squares method, tends to give us a line with a 0 slope. That's an important observation. Suddenly, we can use the slope as a kind of measurement of whether or not there really is something going on. So clearly I'm hinting here that we may be doing some significance testing in a second using the slope. So with nothing going on, a slope of 0 manifests. If something a little more profound is going on, the slope increases somewhat. Notice, as this point here says, once you draw the line, it looks even more linear. Let me go back to when that line wasn't drawn. That looks pretty, pretty weak to the naked eye. Suddenly, that same set of data looks more linear because we have drawn a line there to convince you that it is linear. So be wary that sometimes when people draw a straight line, it convinces the eye that in fact the relationship is stronger than it really is. This is actually a very weak relationship. Okay, so our next set of data, which has a stronger relationship, has this line through it. Let me go back for a second. That and that. Notice the stronger relationship we get, the higher the slope, right? That's not necessarily a rule of thumb, but it's a little pattern that sometimes arises. And here is an even better relationship, our tightest relationship. We have a very strong, profound slope there. Okay, now notice that even though we have a relatively good fit here, meaning it was easy to draw a straight line and it's fairly explainable to our imaginations that there's a straight line there and we have an equation for it, and we can probably make predictions about where it's going to go in the future. Notice that this line really only perfectly describes 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 of these 100 points. So the rest of these 100 points are imprecisely described by this line. There's a difference between each of these points and the line. That difference is a residual. We call that a residual. And in fact, when you add up all the residuals, that gives us a kind of summary error estimate. So in fact, a linear model is this, right? An equation that describes a straight line plus an error, or the residuals. So what is that residual thing? It's not a constant. It's not like I can say, y prime equals 12 plus 5x plus 6. Right? Otherwise, I just add that into my y-intercept. The error is something else. It's a fluid set of factors that actually explain the other things that account for the relationship. What do I mean by that? Think about it for a second. We're attempting here to describe or explore the relationship between vitamin D intake and cognitive function. If we had a perfectly straight line, it would suggest that vitamin D perfectly explains cognitive function. But it doesn't. It's a somewhat linear line. That means that other things also explain that relationship, or also explain cognitive function. Maybe genetics, maybe age, maybe how much schooling individuals had, maybe how much coffee they had that day, maybe how they're feeling that day. There is literally an infinite number of other factors that go into explaining the extent to which cognitive function is predicted by this other variable. So those other factors account for the error. Now, if the error is small, if the residuals are small, then in fact that thing we're measuring, in this case vitamin D intake, is the biggest or one of the biggest predictors of cognitive function. If the error is large, then it's not that important. As we progress using multivariable methods, this error term expands to incorporate other variables. So next week, we're going to look at multiple linear regression. And in multiple linear regression, we'd be plotting something like cognitive function here, vitamin D intake here, education here, age here, and so forth. Each one of these new linear terms are added on to help make a cleaner, more precise, more meaningful estimator of cognitive function. So that's what the error term is. The error term attempts to represent the things that were omitted from the equation that are nonetheless important. We actually call that error term epsilon, and that's the Greek letter epsilon over here. And epsilon will be the focus of the rest of today's very short lecture. The textbook represents epsilon with an E. Why? Because the textbook just likes to be difficult. And I don't know why. They just do that all the time. And it adds up one more thing for me to explain every lecture how the textbook is different from the way everything else is done. Sorry, let me fast forwarding ahead to the computer here. Okay, so it's important to note that every single point on that graph has an epsilon term, an error term associated with it. So here we have the predicted y, and here we have the actual y value. The predicted y is the line that you just drew. The actual line is the dot that we're trying to model. As I showed, only 9 points on that line had these two being equal. Only 9 points had an error of 0. The rest of them had a difference. So each one of those relationships represents an error term. We're going to use that to compute some interesting things. So from our example yesterday we looked at predicting your final exam mark based upon your midterm mark. Remember that? And what we decided was there's a straight line equation where I can predict your final exam mark if I multiply your midterm mark by 0.9 and add 1.5, right? But there's an error term there. So here's how I explore that error term. Okay, so here are the students that I used to compute that straight line, right, from the set that I had from previous years. And this is their midterm mark. This is their final mark. Now, the straight line that I drew from that relationship allowed me to predict a y prime for every value of x based upon that equation. And that's what where I get. I get this value of y prime based upon this equation if I plug in this value of x each time, right? So the difference between this value and that value constitutes my epsilon term, my error term. Notice that sometimes the difference is great, sometimes it's poor. Here the difference is 0. Here it's pretty small. Here it's pretty large, right? So I'm going to write down all of the epsilons here. Okay, that's actually, that's a pretty small set of epsilons in my opinion. So that's a pretty good fit. If I square that epsilon, I get these numbers. Now, why do I square them? Because once again, some are negative and some are positive. All I care about is their magnitude. And so it's a common trick in statistics to square numbers to get rid of that minus sign. We add up all the square values and I get this. The linear regression technique that we're using is one that minimizes that number, minimizes epsilon squared. That's what the technique is attempting to do. Find the line that makes this number as small as possible. And this is the equation that in fact makes this number as small as possible. Okay, this repeats what I just said. The squares of the errors of prediction are minimized. So this is why we sometimes call this the ordinary least squares regression. Now, I mentioned earlier in the year that there is a strong relationship between correlation and linear regression. Specifically, Pearson's correlation, not Spearman's, Pearson's correlation and linear regression. So the larger the correlation coefficient, then the smaller the error terms will be, because the stronger the relationship between these two variables. The more closely linked they are, the less likely other factors are intervening in that relationship. So we're going to compute the standard error of the estimate. One of these new terms you're going to know. And what this is, it's an index of the wrongness of how the line is able to predict values of y. So keep that in mind. It's an estimate of wrongness, or of robustness, if you will, or of precision of that line. And this is the equation for it as a parameter. Put this in your back pocket. We're probably not going to use this one because the parameter estimate uses information from the superpopulation. What we care about is the statistic. The difference again. Remember, the statistic is from our sample, the parameter is from the population. The difference here is that in the statistic, the denominator is n minus 2, and the parameter is just n. So the standard error of the estimate is this equation here. It's just the sum of all the square epsilons divided by n minus 2 under the root sign. And we call this equation the mean square error. Okay, so once it's under the root sign, it's the thing that's not on the root sign, sorry. Without the root sign here, it's called the mean square error. Under the root sign, it's the standard error of the estimate. Whew. Okay, so the standard error is essentially the standard deviation of all the errors, of all the epsilon terms, if that helps you. Probably confuses more than it helps, but that's the official definition of it. So let's compute it. Here's our data again. We've subtracted our y primes from our y. We've got our epsilon terms. We've squared our epsilon. We have our sum of the epsilons. And we are going to now do significance testing. I mentioned when we looked at those 4 different data sets that if there's nothing going on, if in fact there's a random splay between these two variables, we tend to get a zero slope, a straight line, a flat line rather, parallel to the x-axis. So we can use that to do a null hypothesis. We can say that our null hypothesis is that the slope is 0, b is 0. And the alternative is going to be that b is not 0. So this becomes a significance test, a null hypothesis for whether or not the relationship between these two variables is significant. That's all we're testing. Is the relationship significant? In other words, is the slope equal to 0? It's not a, I don't like it. It's not a good way of doing things, in my opinion, but this is the way that the textbook does it, and people have been doing it for generations, so we'll continue doing it. Okay, so to test whether or not the slope is statistically equal to 0, we're going to compute a t statistic, and we do so according to this formula. Very simple. The t is just our slope that we just computed divided by the standard error that we just learned how to compute. And we want to keep in mind that the degrees of freedom for looking up in the back of the book is n minus 2, because we always look stuff up in the back of the book. That's what we do here. So from our example, this was the equation that describes predicting your final exam mark based upon your midterm exam mark. This is our null hypothesis that our slope is equal to 0. We compute our t. Here is the equation. T is our slope divided by the standard error. So our slope in our equation is 0.9, and the standard error was 0.81, if you remember that. We computed a few slides ago. And that gives us 1.11. We look up in the back of the book, and we see in the table is 2.31. As always, since the table's t-value is bigger than our t-value, we failed to reject the null. That was the null. We failed to reject it. That means there isn't a relationship, a significant relationship between the final exam and the midterm, which is crazy because we saw the residuals, the error, the epsilons look pretty small. But this is what it's teaching us right now. So take that with a grain of salt. That's how you do it. I don't like it. So as I mentioned, there is a relationship between the correlation coefficient, Pearson's rho, and linear regression, and this is how that relationship plays out. We mentioned the standard error is this. It's the mean square error under the root sign. This is the root sign here, square root. It says square root there because the person who made this slide, the textbook manufacturer, didn't know how to make a square root sign, I guess. Okay, and that's equivalent to this. That term here is equivalent to that here. What this y in green represents, that's, some people are going to get this confused. Absolutely. What this represents is actually the deviations. So the y's minus the average y, right? So it's the y in the data set, not the computed y, not the predicted y from the straight line equation, but the y in the data set minus the average y from the data set. So remember, you subtract each number, each value of y from the average y. That's a deviation. You add up all of the squares of those deviations and plug it into this equation. So this is equivalent to that. So suddenly, if you can compute that, you can extract this algebraically. How? Like so. I did the math for you. Well, not me. The textbook did the math for you. I'm taking credit for it. So here is how you do it. This is the equation, really, that you need to know. So Pearson's rho squared is equal to 1 minus the sum of all the square epsilons divided by sum of all the square deviations. If you can compute these two, subtract it from 1, you're going to get that. So in our example, we did it. We get 1 minus all that, we get 0.91. That's a very high r squared, despite the fact that we failed the significance test, which is why I don't like that significance test. We actually have a very high r squared. If you remember, this r squared tells us that 91% of the variance in the final exam is explained by what you did on the midterm exam. That's exceptionally high. Okay, so to compute Pearson's rho from that r squared, just take the square root. And square root of 0.91 is actually 0.95, an exceptionally high correlation coefficient. Now, if I plug it into SPSS, I get the same number, 0.955. So we know that's right. So this just repeats what I just said, really. It's the squared residuals is what's left to explain. All this stuff is what's left to explain. And I already said it's explained by the other things. So if we're talking about the relationship between your final exam mark and your midterm exam mark, and I've got this 91% explanatory relationship, the remaining 9% is probably due to, I don't know, the additional studying that you did. Or maybe you freaked out when you got a low mark in the midterm and you came for some extra help. Or maybe you didn't feel well on one of those days or something like that. There are all kinds of small things that are playing a role in how you perform in these exams, but it only counts for 9% according to these data. If you use SPSS for this, just go to Analyze, Regression, and the commands are all there. Notice that the r squared that you get in SPSS is a little bit different than the one that we compute. So they're going to give you an adjusted r squared, 0.901. We just computed 0.91. The reason is the adjusted one just makes a couple of changes because of sample size issues and things like that. But look, they got the same 0.95. Notice that SPSS is using a capital R. There's a reason they're using a capital R. You're not going to use a capital R. A capital R means something very specific that we'll learn about in the next class regarding multiple regression. But SPSS has this default condition where all R's are capital. So here is running that same data in SPSS. We get exactly the same information here. They actually did the significance testing for us. Right. Those are all the slides. Look at that, people. We're done. Let me get out of this stop sharing mode here. Back to me. Hey, me. How come I can't see me anymore? Here we go. Oh, I'm back here. Okay. So those were all of the slides, and that was an incredibly fast lecture. No, half an hour's worth. I see on my Twitter feed that there are no questions. Well, that's good. I'm pretty sure there'll be questions later on. You know how to reach me. I'll see you guys in class on Wednesday, and that is all. Goodbye. Ooh, hang on. Let's add, devil horns. Yeah, that's more like it. Huh? See ya.